Hi guys, in this video what we're going to do is we're going to look at the types of function that we need for this course, and there's three types: injective, surjective and bijective. So we're just going to run through them and see what the differences are so that you'll be able to answer any question on these. So the first type is injective, and if we have a quick look at the blurb on the right here, what we have here, it says every element in X has one image, i.e. one arrow leaving it. So you can see here, look, this is one arrow going from it, this is one arrow going from it, this has one arrow going from it. Now you can see it says no element in Y has more than one arrow arriving at it. So you can see here that 1 is going to 1 and 2 can't go to 1 if this is going to be injective. Okay, now the one thing that we can have here, you can notice that all of my X's are being used, so all of my inputs here are being used, but I don't have to go to all of the outputs in the Y here. So the fact that this 6 is not being used doesn't make any difference. This is still injective. There's also another way of proving if a function is injective using algebraic means, and this is given by this here. I'm not going to go into too much detail about this. I'll show you how this works in a later slide. So one of the tests we can use is what's called the horizontal line test, and it's a bit like the vertical line test we did in one of the previous videos I've done, where in order to check if something is a function, we use the vertical line test. Well, in order to see if it's an injective function, what we do is we use the horizontal line test, where we draw a horizontal line instead of a vertical line, and if it only passes through once, then it is an injective function. So it can only go through at most once, a bit like the vertical line test for a function. The horizontal line test will show us whether or not, if we have a drawn function or a drawn graph, whether or not that function is injective. So now that we've talked about the horizontal line function, let's see this in practice. So you can see here that what we have is a graph A here. So graph A here looks like a quadratic. You can see it's sort of like y is equal to x squared here. And if I draw the horizontal line going through, you can see here that it obviously goes through twice, and therefore the sort of y is equal to x squared graph or function is not an inverse function. Now you can also see here that the domain is all of the real values, so we are saying that this is going to continue in that direction to negative infinity, and this is going to go in that direction to positive infinity. So this is certainly not an injective function. However, if I decide to change my domain, my inputs, and I say, okay, I don't want the domain to be all the real values. What I want for this particular graph or function, all the domain to be just all of the positive real numbers, then my graph will change. So instead of having that lovely curve that we have here, it's going to go from here, because I can't go in the negative direction because my x's have to be positive. I'm only going to go in that direction. Now hopefully you can see, if that's the case, when I draw the horizontal line here this time, it's only going to go through once. So what I've done, by changing the domain, by changing the inputs, I have now made this injective. So let's look at an example. So we're asked here, investigate if the function f, where the inputs are all the real values and the outputs are all the real values, and x maps onto 3x minus 2, is this injective? Well, there's two ways we can do this. We could draw a graph, and I've already drawn it for you. It's a bit rough and ready. Hopefully you can see that if we check this for the horizontal line test, wherever I draw a horizontal line on this graph, and obviously if I carried on up here, then it will only go through at most 1. So therefore we can say that this is an injective function because it passes the horizontal line test. Now, I said to you there's another way to do this using algebra. So this is the sort of mathematical sort of construct for it. But I'm just going to show you by using an example. It's probably easier. So you can see what we have is f of x maps onto 3x minus 2. So what we're going to do is we're going to put x1 through, and we're going to put x2 through. And what we're going to try and show is that once we put x1 and x2 through the functions, it's going to collapse down to x1 is equal to x2. And if that's the case, that means that this is injective. On the next slide, what I'll do is I'll show you when this doesn't work. I was telling you about the y is equal to x squared on the previous slide, so we'll show that y is equal to x squared is not injective. Okay, so let's go for this one. So first of all, do this in blue. We've got 3 by x1, okay, minus 2, And then we've got f of x2 is 3 by x2 minus 2. I'll just tidy this up. It's 3x1 minus 2. And this is obviously 3x2 minus 2. So what we're going to do then is we're going to put them equal together. So we're saying that if f of x1 is equal to f of x2, that implies that x1 is equal to x2. That's just from the definition up here. So I'm going to put those two functions together. So I'm going to put this one equal to this one and then just try and simplify it. So I'm going to end up here with 3x1 minus 2 is equal to 3x2 minus 2. Hopefully now you can see that I've got minus 2 on both sides, so I can add 2 to each side, which means I'm going to end up with 3x1 is equal to 3x2. So all I've done there is added the 2 on this side, I've added the 2 on this side, so I'm left with 3x1 is equal to 3x2. Hopefully again you'll see that what we have is we have a 3 in front of the x1, a 3 in front of the x2. So we have x1 now is equal to x2 because I can divide both sides by the 3 here, and that means I now have x1 is equal to x2, which means that this function is injective. So now I'm going to show you a function that won't be injective. So let's have a look at f of x is equal to x squared. Now, this again, we're going to go from all the real values as our inputs to all our real values as our outputs. And if we graph the x squared graph, it looks something like this, doesn't it? Yeah. Okay. So that's what the x squared graph looks like. And again, we've already done this. I can see by the horizontal line test that this is not going to work. So let's try using the algebraic method. So I'm going to put f of x1, okay, f of x1 is equal to, well, that's just x1 squared. F of x2 is equal to x2 squared. And remember the statement is if f of x1 is equal to f of x2, that implies that x1 should be equal to x2 once we tidy it up. Now, at the moment, what we have is x1 squared is equal to x2 squared. So that's what we've got at the moment. And the only thing we can do in order to get x1 on its own or x2 on its own here is to take the square root. Now, if I do that, problem is that, I'll just give an example if I give you some numbers. If I said to you x squared was equal to 4, and I asked you to square root, or to solve this, sorry, we know this is a quadratic, we know there's going to be two answers, what we should do, and x is going to be equal to plus or minus 2. So again, if I say that this, for example, is 4 here, I'm going to get an answer at plus 2 and an answer at minus 2. Now, that means, on the same sort of logic, if I come down here and do the square roots, that means what I'm going to get here is I'm going to get x1, I'm going to get a plus or minus here because I've taken the square root, is equal to plus or minus, and what I've got then is x2, okay, with the square. They're going to disappear, and I'm going to end up with plus or minus x1 is equal to plus or minus x2. Now, this is where we have an issue, because the issue is we've got here, one of our answers could be that positive x1 is equal to negative x2, and that there breaks this definition, okay, so it contradicts this, which means that this function is not injective. We know it's not injective because we can see it's not injective already on our diagram. So now that we've sorted out the injective definition, let's have a look at the surjective function. So again, here's the blurb, okay, in mathematics, but what does that actually mean in English? So this one here, you can see that every element of x has an image in y. So x, y, this is going to 1 in y, this is going to 1 in y. Every element of y has a corresponding value in x. So you can see that this one is going backwards, this one going backwards, and again this one going backwards. Now, the important thing is every x is 1 arrow leaving it, okay, and every y is used. Now, if you remember with the injective function, we had some values in the y that weren't used, and that was okay for injective. But for surjective, every element in the y set has to be used. If it doesn't get used, then it is not surjective. So there's another horizontal line test for this, and you can see here, in order to be surjective, every horizontal line must intersect the curve at least once. So at least once. Remember, for injective, it could only do it once. For surjective, at least once. So naturally there's an algebraic way to do this, so I'm just going to throw this through to you as well. If we just quickly graph this, so 4x plus 3 is essentially a straight line. We should be happy with that. 4x plus 3 goes through at 3, and there's a sort of angle of something like that, okay? And that's going to continue down towards negative infinity, and it's going to go up to positive infinity. And hopefully you can see that this is injective as well. Now we're going to see, is it surjective? Now, we could do the injective test, but we're not being asked to, so I'll leave you to do that and see if you can prove that this is injective. And the surjective test goes as follows. So what we do is we then start with writing the function in terms of y. So we get y is equal to 4x plus 3. And what I'm trying to do here is I want to rearrange this equation so that I get x is equal to something. So the first thing I need to do here is get rid of the positive 3. So I end up with y minus 3 is equal to 4x. Then the next thing I'm going to do is I am going to divide by 4. So I get x is equal to y minus 3 divided by 4. Now x is all of my inputs and y is all of my outputs. And I'm asking myself the question, is there any number here? Is there any number that I can stick in for y that won't give me an answer for x? Is there any? If there is, that means it's not surjective. So it doesn't matter what I stick in for y here. You can think of any number that you want, and an x value will come out. For example, if I picked 3 for y, 3 minus 3 is 0, 0 divided by 4, x is equal to 0. If I, for example, picked out, I don't know, 7, 7 minus 3 is 4, 4 divided by 4, and that means x is equal to 1. It doesn't matter what value of y that I pick out, it will always give me an answer for x. And that there means it's surjective. So, you knew there's going to be an example for why something wasn't surjective. And at first glance, you're thinking x squared plus 1, where we've got all the real values as our inputs and all of the real values as our outputs. That should work, really. But let's just graph it and see what's going on here. So if we graph x squared plus 1, it's just the x squared graph, and it's just taken up 1, so it looks something like that. And we said that we can do the horizontal line test, so let's do that, and I'm going to do a few of them. So the horizontal line test, that goes through at least once, through at least once, through at least once, and now we've got an issue. Down here, that's not gone through at all. So that means this has failed the horizontal line test when it comes to being surjective. But of course, we should be able to prove this using algebra. And we're going to use exactly the same technique as we did before. So we're going to say, let y equal to x squared plus 1. Okay. We said last time what we wanted to do was we wanted x was equal to something. So we'll take the 1 across to the other side. We get y minus 1 is equal to x squared. And then what we have is the square, which is, we're just going to, x is equal to, and we're going to get square root of y minus 1. Okay, I'm going to ask the same question that I asked you last time. Are there any y values here that we can stick in that aren't going to work? Well, there are, aren't there? Because if I stick 5 in here, that's not a problem. So if I stick 5 in here, I get 5 minus 4. 5 minus 1, is 4, the square root of 4, and x equal to 2, and that's fine. That's fine, it all works. But suppose I put example of y is equal to 0 in here, and I'll just come over to the side here and show what I mean. So if y is equal to 0, what we end up with is essentially 0 minus 1 is equal to x, and that means we end up with the square root of minus 1 is equal to x, which does not give us a real answer. It actually gives us a non-real answer. But if we look at the definition, we said that both of our inputs and outputs, or our domain and codomain, have to be real numbers. So that means that this doesn't exist. So then we might want to start thinking about, well, when or how or where does this thing actually exist? And the important thing is the square root. So this essentially has to be positive. So y minus 1 has to be greater or equal to than 0. And what we're saying here, that y then must be greater or equal to 1. Now, if we look at our diagram above here, you can see that this is the x squared graph plus 1. And you can see that the minimum is 1, and the function exists anywhere, well, God gives an answer of anywhere above 1. Now the easy way to remember if something is surjective is the range is equal to the codomain. So that leads on to bijective function, and a bijective function is essentially if it's injective and surjective. So you can see here that what we have is what's called a perfect one-to-one, i.e. that goes to 1, that goes to 1, and that goes to 1. They're not sharing. 1 doesn't go to 4, 2 then doesn't go to 4. So essentially, there's for one input, there is a unique output. So let's have a look at A and B here. So the curve in diagram A represents a function where all the inputs are real and all the outputs are real, which isn't bijective. Now, it's not injective either. You can see it's not injective. You may think it's surjective to start with, because everywhere that we put a line through, it goes through at least once. But once we come down here, can you see that this particular function can never be negative? However, we're stating that we are expecting it to be able to take all of the real values as an answer or a y value, but that's not the case because obviously it doesn't go underneath the axis here. So we can restrict the domain and the codomain in order to help us make it bijective. So first of all, in order to make this bijective, we need to make it injective, and to do that, I'm going to get rid of this part of the graph, and that's just restricting the inputs, okay, or the domain. So what I'm going to say here is that x is going to be given by a real number where x is greater than 0. Or you could write this, guys, as x is a member of the real family, but positive. Okay? And we're going to have to do exactly the same for the codomain, because the codomain is not equal to the range at the moment. The range is all the possible values that we can have. And the possible values we can have is anything that is above the axes, i.e. anything that's positive. So my y value can only be positive. But we're saying it can take any real value, whether it be negative or positive, and it just can't be negative. But we can turn around and say we're going to restrict the codomain, and we'll do exactly what we did before. So instead of x being a member of the positive real family, we could say y is a member of the positive real family. And that means we've now formed a new function, we'll call it g of x down here. Now this is bijective, because what we've done is we've said, okay, you can see here we've got rid of this part, so that now becomes injective no matter where we go. And it's also surjective because it's taking every positive one. Don't need to worry about it underneath the line now. We don't this, as far as we're concerned, we don't want these answers down here because we only want the positive ones. It's injective and surjective, which makes it bijective. And let's have another look at another one. We'll do this one using algebra, using the two tests. So we will use the injective test first of all. So what we have is f of x1 is equal to f of x2, which will imply that x1 is equal to x2. So let's check that. So the function of x1, so we've got 2 by x1 minus 1 over 3 is equal to 2 by x2 minus 1 divided by 3. Okay, just combine them. 2x1 minus 1 is equal to 2x2 minus 1. And all I've done there now, look, I've multiplied everything by 3s, get rid of these 3s at the same time. So I've got multiply this by 3, multiply by this by 3. I end up with 2x1 minus 1 on the left is equal to 2x2 minus 1. I'm going to add 1 to both sides, so I'm going to get 2x1 is equal to 2x2, and then hopefully you can see I can divide everything by 2 both sides, and I'm going to get x1 is equal to x2, so that implies that this here is an injective function. So there's a good start. So now next thing we're going to do is going to do the surjective test, so we say y is equal to 2x minus 1 over 3, and we want to get x is equal to. So we'll multiply both sides by 3 to get 3y is equal to 2x minus 1. We'll take the 1 across, or the minus 1 across, to get 2x is equal to, and we're going to get 3y plus the 1, and then divide both sides by 2 to get x is equal to 3y plus 1 all over 2. Now I ask myself, is there anything there that I can stick in for y that won't give me an x value, and it doesn't matter what value of y I stick in there, 1, 2, minus a million, 68 billion and 2, 1.6 pi, makes no difference what I stick in there, I'm still going to get an x value. So this implies this is surjective. Now that we have injective and it's surjective, so injective and surjective, this implies that it's bijective. And we're done.